In this segment, we're going to talk about the conservation of mass, which is used when we talk about open systems. So say you're interested in how the properties of a substance change as it flows through a pipe. So here's my pipe, and I've got stuff coming in, and I've got stuff going out. And I want to know, let's say, how the pressure and the temperature change from one location in that pipe to another location in that pipe. Well, I could take the same approach that I've been taking this far in the class. I could take a control mass approach or model this as a closed system. And if I could look at a chunk of mass. If I could just, isolate a chunk of mass that's flowing through there. And let's keep it simple. Let's say there's no deformation or anything in my chunk of mass as it flows through. But it flows through, and I just follow it as it goes from one location to the other. And I look at how the pressure and the temperature change as it does so. Now, since it's a chunk of mass and it's the same chunk of mass, I could say that the mass doesn't change. No mass crosses the system boundary, but I can certainly have energy cross the system boundary. But it'd be a lot more simpler to take a control volume approach, and you'll see why. You could see how the other one would introduce some complexities that maybe we are not wanting to deal with at this particular junction. So here we are, same thing. I want to know how the properties change from one location in the pipe to another location. So what I'm going to do is, instead of looking at a chunk of mass I'm interested in analyzing, I'm going to look at a region of space I'm interested in analyzing. And that region of space is going to go from one location in the pipe to another location in the pipe. Now in this case, I can absolutely have mass cross the system boundary because I've got mass crossing, it's coming in the inlet and it's leaving at the outlet, and energy can cross the system boundary. So let's look at this open system approach. And if we're modeling something as an open system, we need to be able to describe both the mass flow and the energy transfer. So what we're going to need to use is what's called the conservation of mass and the conservation of energy. And these are two of your conservation equations. They're not the only ones, but they're the ones that we'll use in here. So our conservation equations, we've got the conservation of energy, and this is just a fancy word for the first law of thermodynamics. So the first law of thermodynamics says, let's look at that green term. So the changes in energy in that system at some time t. This is the change in energy stored within the system. So when we were talking about closed systems, we said, okay, well, energy could be stored three ways: internal, kinetic, and potential energy. That's what that term is. Then you've got the ways that energy could be transferred across the system boundary. So it is the net amount of energy transferred across the system boundary into the system by, if you've got an open system, by heat transfer, by work, and by mass, because mass itself carries a certain amount of energy as well. Now let's look at our conservation of mass. You'll notice that the wording of it looks really, really similar. Essentially, we've just replaced the word energy by mass. So those conservation equations, they sound really similar. Now, when we talk about open systems, we're often interested in how fast things are happening, the rate at which things are happening. So we can express things in terms of rates, divide everything by a time interval, delta t. Okay, so here, instead of having the change in energy stored within the system, you have the time rate of change of energy stored within the system at some given time. Same thing with the mass, the time rate of change of mass within the system at some given time. So what we're going to do is we're going to focus on that last one for now. We'll get back to the conservation of energy in a different segment, but we're going to focus on the mass for now. So let's look at that first term, the time rate of change of mass in the system at some given time, t. This is dm dt. So the change in mass, you see the numerator, change in mass per unit time. And then the other side of that equation, the rate of mass transferred into the system at some given time interval. So this is the sum of the m dots coming in minus the sum of the m dots going out. And all of this is in kilograms per second. So what are those m dots? Well, that m dot is what's called the mass flow rate. And it's just what it sounds like. It's the rate at which mass is flowing into or out of your system. Let's look at two scenarios. Here what I've got is I've got a system, it's a box, and I've got, I guess, a pipe on either side, a square pipe there, but I've got stuff coming in and I've got stuff coming out. So I've got one inlet and one outlet. And in this particular scenario, the mass flow rate m.1 at the inlet is bigger than the mass flow rate at the outlet, m dot 2. And so what you'll see is you'll see an accumulation of mass within that system boundary because mass is flowing in faster than it's flowing out. All right. And in that case, dm dt is going to be a positive number. Let's look at the opposite. Let's say that the mass is flowing out, m dot 2 is bigger than m dot 1, so the mass is flowing out faster than it's flowing in. Well, then you'll see that system start to empty over time. And in that case, that dm dt term is going to be a negative term. And now let's look at the case where the sum of the mass flow rates coming in and the sum of the mass flow rates going out are equal to one another. I mean, I've only got one of each, but more generally speaking, it would be the sum of the mass flow rates coming in and the sum of the mass flow rates going out. But you can see that since those two things are equal, the amount of mass within that system is not changing over time. And so what we refer to that as is steady state or steady flow. So steady flow indicates that you've got an open system, right? You got stuff flowing in or flowing out. So like I said, no accumulation of mass within that system boundary. And so if I look at this at some initial time and I look at my system and I'm like, oh, okay, I've got 3 kilograms of whatever's in there right now. And then I walk away and I come back a couple of hours later and things have still been flowing. But if things are occurring at steady state, then when I come back a couple of hours later, there should still be 3 kilograms of water or 3 kilograms of whatever substance that's flowing through there within my system. So in that case, dm dt is just equal to 0. And that's going to be the case. Most of the problems that we're going to look at in this class are going to be occurring at steady state, with the exception of this problem. So we've got a device with 3 inlets, 2 outlets, and we're wanting to know, we're given at a given instant, fluid flows in at 2, 3, and 5 kilograms per second and out at 7 and 6, and we want to know the time rate of change of mass in the system at that particular instant. Okay, so here's my device. I don't know what it looks like. It's a box, but there's one inlet. Things are coming in at 2 kilograms per second. There's another inlet, m dot 2, m dot 3, so there's my 2, 3, and 5 kilograms per second. Now I'm going to look at my outlets. So I've got stuff coming out at 7 kilograms per second and 6 kilograms per second. And there's my system boundary. Now I want to know the time rate of change of mass within the system at that particular instant. Well, that's just dm dt. So that's what I'm looking for. Yeah, I don't really have any assumptions right now. Maybe we'll come back to that, but maybe not. Now I'm ready to apply my conservation of mass. So if I apply my conservation of mass, dm dt is equal to the sum of the m dots coming in minus the sum of the m dots going out. Well, I've got 3 inlets and 2 outlets. So my inlets are 1, 2, and 3. My outlets are 4 and 5. And if I just plug in the numbers, I ended up getting a negative 3 kilograms per second. So what that tells me is that it's a negative number, so mass is flowing out faster than it's flowing in. So, okay. Well, I hope that was helpful, and thank you for watching.